once again welcome back to my YouTube channel. This is Unit 3 Magnetic Effects of Current and Magnetism for class 12th, and today we will be finding the expression for magnetic field at the center of current carrying circular loop. So before finding the expression for the magnetic field at the center of current carrying circular loop, we will be trying to understand the condition with the help of one animation. So first of all, we will understand how the current is flowing through the circular loop, and then we will be finding the expression for it. So let us say in this circular loop, the current is flowing in the anti-clockwise direction. Now we know in physics we cannot study this thing all at once. Therefore, we will have to divide this circular loop into infinite number of equal parts such that the length of all the parts is same. So we will consider one small portion of small length dl which is lying at distance small r from the center of the circular loop. Now current was flowing in the anti-clockwise direction, so the tangent at dl will give us the direction of current, and this will be our current element such that it will form the angle of 90 degree. So now this condition is clear to us, and now as we have considered only one portion of length dl which is under study, therefore for this small portion we will be having small magnetic field which is produced by this small current element of length dl. That is, the current element is IDL, which is producing a very small amount of magnetic field at the center of the circular coil. So in order to find the magnetic field at the center of the circular coil due to this small element, we will be applying Biot-Savart law. According to Biot-Savart law, we have dB is equal to mu naught upon 4 pi IDL sine theta upon r square. So let us write the expression for it. Mu naught upon 4 pi IDL sine theta upon r square, where mu naught is the permeability of a free space. Now here, as we have already discussed with the help of animation, that theta is equal to 90 degree, therefore our expression turns out to be dB is equal to mu naught upon 4 pi IDL sine 90 upon r square. Now we are aware about the value of sine 90, that is sine 90 is always equal to 1. Therefore we will substitute this value in the above equation, and we have dB is equal to mu naught upon 4 pi IDL upon r square. So this is the amount of magnetic field which is produced by the small portion, but we are having infinite number of equal parts which are producing the same amount of magnetic field at the center. That means we have to find the total magnetic field, that is, it is given by integrating the above equation. By integrating, we mean we are adding up the magnetic field produced by all the small portions. So total magnetic field B is equal to integral of dB is equal to integral mu naught upon 4 pi IDL upon r square. Mu naught upon 4 pi could be taken out of the integral, being constant, and also constant current is flowing through the loop. Therefore I upon r square is also taken out, and we are left with integral dl. If we will add up all these small lengths, it will turn out to be a circular loop. For circular loop, we know the circumference represents the total length of the circle, or we can say that the total length of the circle is the circumference of a circle. Therefore we write B is equal to mu naught upon 4 pi I upon r square and 2 pi r, which is the integration of dl. We will cancel out pi and we will cut down the 2 and 1 r. We are left with B is equal to mu naught I upon 2 r. So this is the expression for the magnetic field which is produced at the center due to current carrying loop. Now our loop was having no number of turns. There were no turns in this magnetic loop. So if there are no turns, therefore we are having B is equal to mu naught I upon 2r. But if our loop is containing n number of turns, then the magnetic field will get n times. So then in that case we have B is equal to mu naught Ni upon 2r. So this is the magnitude of magnetic field which is produced at the center of the current carrying loop. Now we need to determine its direction as well, because we are having a magnetic field which is a vector quantity, so definitely it is having a direction. In order to find out its direction at the center of the loop, that is the amount of magnetic field having a certain direction at the center of loop, we will have to apply Fleming right hand thumb rule, or we can say it as Fleming right hand curl rule. We will again understand it with the help of animation. If the current is at this point, we will place the right hand in this way and curl our fingers. The fingers are acting in inward direction. If we will move to the upper portion and again place the right hand in the direction of current and curl our fingers, again these fingers are acting in the inward direction. Similarly, on the right side, the current is flowing in the downward direction, and if we place our right hand and curl our fingers, the fingers are getting inwards, so they are entering the center O. So in each case, the direction of magnetic field lines is coming out to be acting in the inward direction, and they are acting perpendicularly. So we can say that the direction of magnetic field which is produced by the magnetic loop is given by Fleming right hand rule, which is inward and perpendicular. So